Okay, this first part of the problem asked us to compute the velocity in the thin tube of air. Now notice that you started out roughly with pressure here equal to atmospheric pressure, and velocity equal to nothing. And then you squeeze this closed. Velocity we discovered was something like 1,500 centimeters per second through this little orifice. Now, what about the pressure? Well, this is the Bernoulli equation, and it really applies. This equation essentially applies to a fluid, and in this case, the fluid is the air that we are looking at manipulating with this bulb. And notice that we don't change in the position. We start out y1 here, y2 is at the same position. So I just dropped out those terms just to make this simpler. So we have the static pressure plus the velocity equals the pressure over here plus the velocity. Now notice this velocity in the beginning is essentially nothing. It's sitting there. And suddenly we squeeze this bulb. The velocity shoots through the roof. Well, how have we gained this energy, this dynamic pressure? Well, we gained it by paying for it from this pressure here. We've basically lost a whole bunch of pressure in order to give those molecules velocity. This pressure P2 is very small, and that's actually what causes the vacuum that's created here and causes the liquid to come up here and be misted out, this perfume mister. So the question is, the second question, how fast does the air need to travel in the thin part of the tube up in here in order to get the perfume pulled up the 10 centimeters? Well, this is the equation that we need to kind of look at now, is that we know we've got to pull this thing vertically 10 centimeters. That means we're fighting gravity and using the density of the liquid, pulling it up 10 centimeters. What is the change in pressure? What's the initial pressure? Well, it's probably atmospheric pressure. So P1 is atmosphere. And then what is this delta P? Well, dP must equal the density, what we're going to call that 1 gram per centimeter cubed, times gravity, let's call it 10 meters per second squared, times the change in height, 10 centimeters. So we need to keep these units together. So it's going to be well, I can't convert very well here. 10 centimeters, I need to erase that. 10 centimeters. And now we've got a mixture of units. I need to convert those centimeters. We know 100 centimeters constitutes a meter. And we know that, oh gosh, we got to convert this 1 gram per centimeter. We know that 1,000 grams is a kilogram. And we also know that 100 centimeters is a meter, and we need to cube that in order to cancel out these units. That enables us to cancel out centimeters cubed. Then we have centimeter here, gram there, and we're left with the delta pressure is equal to, let's see, I'll collect all these terms. We have 10 times 10 divided by 100. That's this one. Okay, that drops out. Then we have 10 squared to the third power divided by 10 to the third. That's this one here. 10 squared to the third power over here, divided by 10 to the third over there. And this is equal to 10 to the 6 minus 3, 10 to the 3, 10 to the third, so 1,000. And the units should be kilogram meters. Nope, kilogram per, we have meters here, meters squared over here. Let's see, meters squared, meters cubed on the bottom, so kilograms over meters second squared on the bottom. Okay, the centimeter cubed here cancels with that one. So we have meters over second squared, kilograms, and then we have meters cubed. So, what's that doing there? That's nothing. So, in other words, this is the same units as kilogram meters per second squared, which is a Newton per meter squared. Newtons per meter squared is equal to pascals. So the answer, oh my goodness, is 10 to the third newtons per meter squared is the change in pressure. So it started out with, that's the difference in pressure. The question was, how fast does it have to travel in order to pull it up 10 centimeters? Well, we know the difference in pressure must equal 1,000 newtons per meter squared. And it starts out as an atmosphere. So it must be an atmosphere minus 1,000. So let's keep going here. I need a clean sheet of paper here. I'm going to pull one up here. Oops, it's not clean. So we have 10 to the third newtons per meter squared equals dp equals 101,325 newtons per meter squared minus the new pressure. So the new pressure equals 101,325 minus 1,000 is 100,325 newtons per meter squared, which would be the pressure that it would need to be in order to pull that water up. So the question was, what is the velocity that is required? So if we go back to the Bernoulli equation, we know P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. We established that the initial velocity essentially is nothing. This is one. Well, I guess what we did is we calculated the P1 minus P2, which is this value right here. P1 minus P2 is 100,325 newtons per meter squared equals 1/2 rho times V2 squared. Now notice we did something funny here. We crossed from one system to another. So we started out saying that we needed to get a vacuum in this throat here. And we computed the dP, or the size of the vacuum. dP is 1,000. Actually, I need to go back and change that. It's 1,000 newtons per meter squared. That's the difference in pressure in order to pull this guy up. Again, starts out as atmosphere. It needs to be 1,000 newtons per meter squared less than atmosphere. Now we jump over and say, okay, what does this velocity need to be? Well, this is a different gas altogether, a different fluid. This fluid right here is pressed through here at a velocity, and the pressure drops in order to accommodate the energy gain in this velocity. So we know the pressure has to drop. This pressure minus that pressure must be 1,000 newtons per meter squared. So I go back. To here. Actually, I'm a little bit tired, so this is not making sense. So let's do this. P1 minus P2 equals 1,000 newtons per meter squared equals 1/2 rho V2 squared. So V2 equals the square root of 2 times 1,000 newtons per meter squared divided by the density. That equals V2. So What the heck is that? So V2, the density. That would be the density of air.